Greetings and welcome, friends. Today we're going to discuss sample sets of data. All right, sample sets of data. And to start off, let's talk about some concepts. In statistics, let's talk about what I mean by population. All right, and population in statistics does not always refer to a group of people. All right, it refers to the entire set of values being considered. All right. All right, so it does not have to be a population of things. It could be I measured the widths of all of the desks in my room. So the population would be all of the desks in my room, right? So it doesn't necessarily have to be a group of people or animals to be a population. All right? So that's the first thing here. And when it comes to gathering data on a population, oftentimes it's not feasible to survey or gather data off of the 100% whole population. Okay? So imagine like if I was trying to estimate the population of deer in the Green Mountains. I'm not going to actually go out and wrangle every deer in the Green Mountains and like gather data on it to figure out how many of them are older than 2.5, right? I'm going to only, at best, get a portion of that population, okay? In fact, twice in the last year, two separate gentlemen from the United States government, the Census Bureau, have come to my house to gather data on my family, all right? And they didn't actually have my name even when they showed up. They had apparently some computer program that randomly gave them addresses of people in Windham County, and then they'd show up and then gather data. And so they were gathering all sorts of economic data and unemployment data. I just said data and data two different ways, but that's fine. Waldo right there. So what they were doing was they're going to end up coming out with statistics at the end of their study that would say like the median or the mean annual income or salary for a household in Windham County is blah. And they didn't actually go out and gather that data from every single household in Windham County. They gathered it from a subset of the true population, and they're going to kind of make conclusions about the whole population as a result. Now, if they only surveyed my household, would they have some good results? No, because surveying one person is not going to be good at making a generalization about the entire population. All right, that would be like an anecdotal incident, right? That would just be like a single story, but that doesn't tell the whole story. All right. So what they do is they take a random sample of the population. So here's what a random sample is. All right. So it's a portion of the population that is selected to represent the entire population. Of a population that represents the entire. All right, and it's really important that this is random. Now consider, what if I was doing a survey trying to figure out how many students in our school exercise at least 2 hours a week, right? And let's say I was like, I want to gather some data. I can't get the whole population, but the basketball team's practicing today. I'm going to just show up at basketball practice, ask those kids. That'll maybe hit like 15% of our population or whatever, and then I'll extrapolate that data to the rest of the population. That would be a bad sample. Why would you think so? Because they're on the basketball team. It's not random. That would have been me hitting one targeted subset of the population, which is probably going to skew my data, right? I'm probably going to end up saying like, wow, 95% of Twin Valley High School students exercise at least 2 hours a week, and that's probably not a true statistic, right? Because I didn't have a truly random sample, I ended up choosing a subset that had too many things in common, too many they're not coincidences, but there was too much of a correlation between the sample that I picked and the data that I was trying to conclude on. All right, that's why when they're doing polling after or during, I guess, a presidential election and other elections, they'll do what's called exit polls. Well, at different locations across the United States, they'll randomly survey people after they already voted, if they're willing to, and they'll just say, are you willing to tell us who you voted for, what you voted? And they'll get a portion of the population, and based on the trends of that portion, they could start to predict, all right, so-and-so has, 47% of the vote, and then they'll usually have like plus or minus a 1% error or something like that, right? So the key is getting a random sample. Now, once you have a random sample, you can do what's called inferential statistics. All right, and with inferential statistics, it is using information gathered in a sample to make predictions about the population. To make predictions about the population. Okay, so it's key that the sample is random. All right, and then once I have that random sample, I can get exact statistics about my sample, and then I'll end up extrapolating those results to the entire population. Is the idea. So the more random that my sample is, the better it represents the entire population in theory. And the other concept that we'll be working with today is that the larger my sample, the more likely it represents my entire population. Okay? So the more people I survey in my sample, the more data I gather from my sample, the better it will represent the entire population, because it's less and less likely that I'm just getting some obscure results, right? So let's say I started by surveying the basketball team, all right? That's not truly random. And it would skew my results one way. But then the next day I decide I'm going to go to the cafeteria and start surveying people there. And now the more people I survey, the better my data is going to be representative of the population. It will start to get away from that skewed result from the beginning, right? And it's a matter of actually probability. The more people I survey, the more likely it's going to represent the entire population. Now, what we have to kind of measure our accuracy, I guess, is called, I guess within our population there's a couple things we need to know. The true mean of my entire population is referred to as the Greek letter mu, all right? So that's read as M-E-W, all right? So it's kind of like this weird little mu, right? And actually my best friend used to call his cat's name was Mewy, and whenever he'd write it out, which I don't know how often you write out your cat's name, I guess, like writing letters in the morning for when the cat wakes up. Like, hey Mewy, have a great day, love you, bye. Well, either way, he would write it out with this Greek symbol mu, which is also representative of the coefficient of friction, by the way, in physics. So the true mean of the population is mu. The mean of our sample we'll refer to as x bar. All right? So we end up having an exact representation of the mean of our sample. The true mean is going to be some unknown to us unless I actually gathered 100% of the data from my population. All right, but that often is not able to be done, right? It's just not a reasonable thing to do, is often the case. So where this is going to come into effect is what's referred to as the standard error of the mean. So standard error of the mean. Okay, and it's a standard deviation of the distribution of the sample means of the sample means. And what it's measuring is how likely is the true mean within a certain range of my sample mean. Okay, is the idea. And so our formula for it is, it's actually got its own symbol. It's sigma sub x bar. And it's equal to the sigma of our sample over the square root of n, where n is the size of our sample population. All right. So sigma is the standard deviation of the sample. And n is the number of values in the sample. Okay, so and the smaller the standard error of the mean is, I guess I'll write that out. That's also read as sigma sub x bar is how you could read that symbol if you wanted to, or you could just refer to it as the standard error of the mean. All right, same difference. But I want to point out is that if I survey a small portion of students, the broader my sigma sub x bar is. But the larger n becomes, the smaller the sigma sub x bar is. All right, so if I survey 4 people, I'd get the square root of 4, and sigma sub x bar would just be half of my standard deviation. If I survey 100 people, square root of 100 would be 10, and it would just be 1/10 of the standard deviation. Right? The more people I survey, the more data I gather, the smaller the standard error of the mean is. So it's going to basically be making it more and more likely that my true mean is within a certain range of my sample mean, the x bar. Okay? So let's actually put this to use. Let's see what this looks like. So what if I say find the standard error of the mean in this population? So let's say I have the following. Let's say that n is equal to 100. Let's say that our mean of our population, or sorry, subset of our population, our sample, let's say that's going to be 60. And let's say the sigma of that population is 12. Okay? So if I want to find the standard error of the mean, let's see, what's my formula? Sigma sub x bar is equal to sigma divided by the square root of n. Right? So all I have to do is kind of plug in these values, and it'll give it to me. So that would be 12 divided by the square root of 100. That's 12 divided by 10, or 1.2. So let me show you what this means. I'm going to draw 2 graphs. All right, because the standard error of the mean is a type of standard deviation. All right, let's see. I'm going to have 2 of these graphs here, side by side, or top and bottom. Let's see, make sure you guys all get that information. So let's write down what we know. So for our regular distribution of the data, all right, that's what this graph will be. So the distribution of our data values, okay? I would have, let's see, the mean was at 60, and the standard deviation is 12, so one standard deviation above would be 72, two standard deviations above would be 84, one standard deviation below would be at 48, and two standard deviations below would be at 36, and so forth, right? So this is the distribution of our data, how it would land if it happens to be normally distributed, okay? And then this graph is going to be the distribution of our means, all right, of our possible true means, okay? So the sample's mean was 60, and it would be really great if that actually was the mean of the entire population, but that's unlikely, all right? And now sigma sub x bar is 1.2. So that means 1 sigma sub x bar above would be 61.2. 2 sigma sub x bars above would be 62.4. All right. 1 sigma sub x bar below, that would be what, 58.8? Did I do that right? Yeah, plus 0.2 and then plus 1. I like it. And subtract another one, 2 sigma sub x bars below is going to be 57.6. So this is the distribution of the true mean. So this tells me that the true mean is somewhere between these values, okay, with the same percentage distribution as a regular normal curve. All right, so here's where our data lies. So I could say that 68.3% of our data is between 48 and 72. Similarly, I could say that the true mean of the population, there's a 68.3% chance that the true mean, the mu, is between 58.8 and 61.2. All right, I could actually, even if I wanted, graph these on top of each other. So let's see, here's 60, there's 61.2, there's 62.4, and there's the others. If I graph these on top of each other, this is what it would look like, where it would be extremely unlikely, and then it would skyrocket here, and that's really sad looking, but it gives you the idea. The purple graph would be the distributions of my data, right, where I could say, the true the distribution of the data is of our sample. And then the green graph is where is the true mean. All right, so if I want to narrow this range, if I want to make this even more accurate, if I want to make for certain that my true mean is between, say, 59 and 61, so that I'm 95% certain, I could actually do that, and it would just be related to improving the number of people that I survey, is all that I would have to do. Okay, so that's what sigma sub x bar is representing. It's the standard error of the mean. It's a type of standard deviation in reference to where is our true mean compared to our sample population's mean. All right, I know I've probably said that a bunch of times, but I just want to make sure it's worded clearly for you. So let's put this to work. All right, let's put this to work. What if I want to say this? Determine the interval about the mean. Maybe I'll snapshot this right here. And I'm going to go to the next page because I'm going to run out of room. So let's do this. Determine the interval about the mean. That the true mean is, let's say, 95% likely to be in. And there's our setup. So, if I want to figure that out, now let's see. Let's look at some keywords. I see the word interval and about. So I'm thinking that's an above and below situation. So that's going to be like a t-value, all right, because I see the word about there, about the mean, right? So I'm thinking about t-values here. And I know I want to be 95% certain that the true mean is between that value, so p is going to equal 0.95. So I want to figure out what is the interval that the true mean is between, where I'm 95% certain that it's between those values. So what I can do is look up exactly the same charts that we've been using. All right, I'm going to look up, let's see, a t-value of 0.95. It's going to be somewhere between those, right? Or actually, wait. Sorry, I lied. 0.95. I know the percent, but I don't know the t-value. I lied. Here it is. Bam, right there. So I look up the percent that I wanted, and here's the corresponding t-value. Here's the corresponding z-value. I wanted the t-value because we're talking about the mean. So when p is 0.95, t is apparently 1.96, we'll call it. So that means 1.96 standard deviations above and below the mean. I'll be 95% certain, right? 95% chance that my true mean is between there. So if I want to find that interval, well, I'll be able to actually use the same little calculations we did on our homework, where I could just find an interval, x bar plus or minus t times, and instead of sigma, I'm going to multiply by sigma sub x bar, the standard error of the mean, right? So let's see. So let's calculate this. So what does this look like? Well, my mean of the sample was 60. I'm going to add and subtract 1.96 times sigma sub x bar was 1.2. So it literally behaves like a standard deviation. All right? It's just a separate type of graph that's representing the likelihood of the true mean being within that area. Okay? Is the idea. So let's do this. 1.96 times 2. And I get 3.92. So I'll do 60 plus that. So the upper end of my interval is 63.92. The lower end of my interval would be the same thing, subtract that, and I get 56.08. So what this is saying is that I'm 95% certain that the true mean is between 56.08 and 63.92. Okay? I'm not 100% certain. And there is a 5% chance that it's not between there. Okay? But because this is a standard, a normal curve, right, and this is a type of standard deviation that I'm working with, right, there is a chance that my true mean is way over here, right? There is a chance that my true mean's at like 63.6 or whatever. But it's not that likely because this is getting less and less likely as time goes on, right? As the further out I get from my sample mean, it's less likely that the true mean's there. So that the way I can actually narrow these down, like I said earlier, is if I just start gathering more and more data, this is going to become a narrower and narrower curve over time. It's just going to get less and less likely, and I'll be more and more certain of the proximity of the true mean. So the last concept we're talking about, and we've actually already done it, but it's just phrased in a weird way, is called level of confidence. All right. Typically there's two that we use, but it's the level of confidence is the probability that the true mean, the probability of the true mean, sorry, Same difference, I guess. Being within a certain range of a sample. So it's kind of what we were describing, right? I was 95% sure that in the previous problem that the true mean was between those values. Now the weird thing about level of confidence is the two frequent ones that are used is a 5% level of confidence, I'll call it LOC, means 95% certainty. And a 1% level of confidence means a 99% level of certainty. Okay? So it's, I kind of think it's weird that they worded it that way. I'd rather call this a 95% level of confidence, like I'm 95% confident of this, but they actually phrase it in the kind of the opposite way, I guess. So, so that's the main thing you have to be aware of. So for the same problem, if I wanted what interval, I guess this is another example, what interval has a 1% level of confidence, LOC, that looks like LOL, that's fine, bam. Well, what would I do? I would look up the corresponding, right, that means P is 99%, right, or 0.99, and we're usually always talking about intervals about the mean for this. It doesn't necessarily make sense for a z-value, I guess, unless you're in manufacturing or something like that, where maybe you're manufacturing parts and you're trying to get certain components to be exactly 1 centimeter wide, and maybe it's okay if it's less than that. But if it's like 1.02 centimeters wide, maybe it just fails miserably and whatever you're building with it does not work. So in that case, you'd actually be interested in a z-value to some effect. But typically, we're always interested in some t-values here for this stuff. So I'd be interested in what's the t-value when I have 0.99 as my percentage. So I'd look at my third chart over here, 0.99. I get 2.58, I guess I'll call that. So I'd look that up, bam, and I would have t equals 2.58. So to find my interval, all I have to do is the same little calculation. I do my mean, and I'm going to add and subtract my t times my sigma sub x bar, right? This tells me how many units to go above and below the mean. By adding and subtracting it, it gives me an interval, right? So referencing the same original problem, that would have been 60 plus or minus 2.58 times 1.2. And notice sigma sub x bar behaves exactly like a regular standard deviation. Same exact idea, because it actually is a standard deviation. So that's the same as 60 plus or minus 3.096. So I'm going to do 60 minus 3.096, and I'd get my interval's lowest point, 56.904, to adding that to 60, and I get 63.096. And there's my interval in which my level of confidence is 1%, which sounds bad. It means that I'm 99% certain that the true mean is between those 2 points. So that's the idea regarding sample sets of data. There's a lot more that can be done with it in kind of upper level statistics. We're just considering the location of the true mean, all right? And that's all that we're considering for this. So it's not too bad. It behaves exactly like a standard deviation. You guys are good, right? You could even draw a separate graph for each of them. Have a great day. Bye-bye.